chi-square goodness of fit test, I will introduce the concepts, calculator instruction, and everything you need to know in this video. So after finish watching this video, you will be able to finish a different problem all by yourself. So for chi-square goodness of fit test, the question that we are trying to answer is, does an observed frequency fit an expected frequency? Simply speaking, that means, does what you saw fit what you thought? So what is observed frequency? Observed frequency, like you run an experiment and then you collect some data. So those data, they are the observed frequency. And then expected frequency is what you expect to happen. So for the expected frequency, all you have to do is you drop down your thoughts. You don't need to collect any data for that. So let's say I conducted an experiment, my observed frequency is 10. So that means I did something and then I collect a data. So 10 is my observed frequency. And then let's say, okay, I collected a 10, but I expect that 12 will happen. So 10 is my observed value and then 12 is my expected value. I collected a 10, 10 happened in real life, but I expect that 12 will happen. So 10 is what you observe, 12 is what you expected. So let me give you another example. So for example, let's say you roll a 6-sided die. So 1, 2, 3, 4, 5, 6, 6 faces. So the probability to get each face value is 1 over 6, right? You roll a die, what is the probability to get a 2? The answer is 1 over 6. You roll a die, what is the probability to get a 5? The answer is 1 over 6. So suppose the die is not manipulated. So the probability to get a 1, 2, 3, 4, 5, 6, so either one of the 6 faces is 1 over 6, okay? So if you roll a die 60 times, that means do you get 10 outcomes for each? Do you get 10 outcomes for each face value? Okay, what does that mean? Let's take a step back. So let's say you flip a coin. What is the probability to get a head? 1/2. What is the probability to get a tail? 1/2. Okay, 1/2, 1/2, right? 50-50. So if I flip a coin 10 times, that means I will get 5 heads and 5 tails. So the 5 heads and the 5 tails, they are your expected frequency. How about the observed frequency? Observed frequency is you have to pick up a real coin, flip the coin 10 times, and then write down how many heads and how many tails. All right, so in this experiment, I rolled a die 60 times. So let's take a look at the table. So the first column, I roll face values, right? So face 1, 2, 3, 4, 5, 6, you have 6 different outcomes. And then in theory, the probability to get a 1 is 1 over 6. The probability to get a 2 is 1 over 6, so on and so forth. And then the observed frequency, that means I have to pick up a real die, a 6-sided die. I have to pick up this die, roll 60 times, and then write down the result. So let's say I got 11 copies of 1. I got 1 11 times. I got 2 8 times. I got 3 6 times. I got 4 13 times. I got a 5 10 times. I got a 6 12 times. And then the expected frequency is you take the total, which is 60, and then you multiply the expected, the percentage, the probability. So 60 times 1 over 6 is 10, 60 times 1 over 6 is 10, and then we have 10, 10, we have a 10 for each face value. And then one other thing that I have to remind you, since the expected value, so the expected percentage, they are all 1/6, which is the probability. Sometimes the problem will use this word, they will say the expected percentage is uniformly distributed. So if you see the word uniformly distributed, that means for each category, all categories have the same probability. Again, for uniformly distributed, if you see this word uniform, means every single probability is the same. So uniformly distributed means every face value has the same probability. All right, so when you do a chi-square goodness of fit test, the expected frequency, you have to do this yourself. The problem, usually they don't provide expected frequency. So you have to take the total, which is the sample size. You roll a die 60 times, right? If you roll a die 600 times, then that will be 600 times 1 over 6 and 600 times 1 over 6 for each face value. If you roll a die 1 million times, that means you have to take 1 million times 1 over 6 for each face value. And then for a chi-square goodness of fit, so since this is a hypothesis test, there is a null hypothesis and there is an alternative hypothesis. So for the null hypothesis, the the null hypothesis, we always say that the observation fits the expectation. What you see fits what you expect. And then the alternative hypothesis is the opposite. So you say what you see, the observations, they do not fit the expectation. So this is the easiest way. So every time I do a goodness of fit test, this is what's in my mind. H0 is fit, HA is not fit. How about this? Write this down. When you do a goodness of fit test, chi-square goodness of fit, H0 is fit, HA is not fit. So that is the easiest way to memorize H0 and HA, fit versus not fit. And then in general, so for H0 in a complete sentence, you have to say the observed distribution or the data fit the expected distribution. So fit and not fit. The HA is the observed distribution. You use the same sentence. The only difference is you change the fit to do not fit. So observed do not fit expected versus observed fit expected. So that is for H0 and HA. Of course, since this is a dice problem, you can modify the sentence a little bit and then put that in the context of the problem. And then the next step is, so for chi-square test, so do you still remember that for the z test, so for normal distribution, there is a probability density function for the normal distribution, right? There is a way to calculate the z value for one sample and two sample. And then for the t-test, there is a formula to calculate the t value, right? Which is called the test statistics. And then for the proportion, there is a way to calculate the test statistics. Still remember that? The z procedure, the t procedure, and the proportion, there is a way to calculate the test statistics, and then the test statistic leads you to the p-value. And here is the formula to calculate the test statistics for chi-square goodness of fit. So you have to write a chi-square. So this is a chi-square symbol. So it starts with this, and then a straight line, and then a square. So this is a chi-square. This is a Greek letter, chi-square, that equals to sum. So this is called sum. Sum of what? Sum of observed minus expected square the difference divided by expected. So I make this simple. I say O minus E squared divided by E. And then you do this for every category. And then you sum up all the results. And then for this, I will later on in the video, I will just show you how to do this step by step using the table above. And then the degree of freedom is the number of category minus 1. And then we have a test statistic, right? We have a degree of freedom. All right, in order to figure out the p-value, I need to look at the graph, right? Left side, right side, two side, and I have to calculate the area under the curve. So that leads me to the graph of the chi-square probability density function. So this is the chi-square probability density function, PDF, that is called f of x equals to a very complicated function. So if you say, alright, I haven't taken any higher level math, I don't understand what this function means. So just take a quick look. So this symbol is a gamma function, and then the V is degree of freedom. If this is your first time learning chi-square, don't worry about memorizing the PDF. For the normal distribution and the t distribution, do you still remember the probability density function? You don't, right? So every time I mention normal distribution, all you know is a bell curve. So that is good enough. For chi-square, don't worry about memorizing the PDF. Okay, don't worry about it. Just take a quick look. We have a gamma function, and then V is the degree of freedom, and then this function has a graph. And then the shape of the graph is determined by the degree of freedom. So the degree of freedom affects the shape of the curve. Okay, so whatever that degree is, affect the shape of the curve. So what is the curve look like? Still remember that the normal distribution has a bell curve, the t distribution has curves. That the curve, the shape is changing depending on the degree of freedom. So similarly, for chi-square probability density function, the degree of freedom affects the shape as well. So I cannot give you one curve like the bell curve. I have to give you multiple curves. And then the shape of the curve all depends on the degree of freedom. So let's say when the degree of freedom is equals to 3. So degree of freedom is equals to 3, so you have a red curve. So that is a small degree of freedom, so you have a big peak on the left, right? You have a very tall mountain on the left. And then when the degree of freedom is equals to 5, it looks like the peak drops a little bit, right? And then when the degree of freedom is equals to 10, that looks like a normal shape mountain, or you can say, I won't say a bell shape. One thing that I will do is keep in mind the curve changes all the time, the shape changes all the time. I won't waste any time to memorize the function. Okay, so for the function, just don't worry about it. Don't waste your time to memorize. When I say chi-square, okay, chi-square probability density function, just keep in mind that you have some curve that looks like this, the shape looks like this. And then if you don't even remember the shape, don't worry about it. Just remember, degree of freedom is very important. That changes the shape of the curve. That's it. Degree of freedom affects the shape of the curve. All right. So now, go back to my table. So I have the same table. How do you perform a chi-square goodness of fit test? So here is how you do it. So usually, the problem will give you the observations, which is the face value, and then the expected percentage, and the observed frequency. So the problem provides the data, some percentage, and then the name of each category. And then what you have to do, the first step is you have to calculate the expected frequency. You have to take the sample size, which is the total, the sum of observed frequency. So the sum is equals to 60, right? So the sum is equals to 60. And then you take the 60 and then you multiply each category. So you take the 60, multiply the probabilities, and then you get a bunch of expected frequency. And then the next step is you turn on your graphing calculator. So the first place that you will have to go is follow the first screenshot. You have to click the stat key. So where is the stat key? The stat key is on the left-hand side of the left arrow, STAT. You hit the stat key, and then you see edit. You will see the menu in edit. You hit stat, and then you hit edit. So once you hit edit, you see some columns, right? L1, L2, L3, L4, L5. So if you have data that you don't want to use, just move the cursor. Just hit the up arrow. Move the cursor to the top of L1, L2, or L3, and then hit enter. Hit clear, and then hit enter. So move the cursor all the way up, hit clear, and then hit enter. That's how you clean up the entire column. So for this problem, I will put the observed frequency in L1, the expected frequency in L2, and then that's it. Observed in L1, expected in L2, the expected you have to do that yourself. And then the next step, we will go ahead and carry out the test. So the correct place to go is follow the screenshot. Do you see that I says hit stat, and then you go to test? So you hit the stat key, and then you go to test. Hit the right arrow. You go to test, and then you go all the way down until you see chi-square GOF test. So GOF means goodness of fit. And then if you have a chi-square test, the one above, that is for chi-square test of independence. That is another kind of chi-square test. So GOF, goodness of fit. And then you hit enter, and then they will ask you the column for observed, the column for expected. I put observed in L1, expected in L2, and then the degree of freedom, how many categories? I have six phases, right? Then you take 6 minus 1. That is called degree of freedom. I prefer to type 6 minus 1. When you hit the down arrow or the enter, they will do the math for you. But when I show you a screenshot, I will just hit 6 minus 1, so you know what it is. So the number of category minus 1. The color, if your calculator has a color, pick any color you like. So when you hit calculate, they will give you the next menu. The next menu gives you the chi-square test statistics and the p-value. If you click draw, they will just give you the draw. And then the p-value is always on the right side, because chi-square goodness of fit test is a right-sided test. So let's take a look at the chi-square. So the chi-square is equals to 3.4, and then the p-value is pretty big. That is greater than 5% alpha, assuming alpha is 5%, so that means we fail to reject the null hypothesis. And then if you click draw, they will give you the chi-square on the bottom of the screen, and then the p-value, and they will shade the p-value for you, right? And then how do they get the 3.4? So back to the z-test and the t-test, all you have to do is you plug in numbers, right? But in a chi-square goodness of it, the plugin is a little bit more complicated. So let's take a look. We have a chi-square, right? We have a chi-square, and then the sum of observed minus expected square divided by expected. So how do I get this number? We do this column, we do this row by row. So the first face value is 1. So go back to the table, look all the way to the top. The expected frequency is 11. So the observed is 11, the expected is 10. So you take 11 minus 10 squared divided by 10. Face value 2. Observed is 8, expected is 10. So you take 8 minus 10 squared divided by 10. And then the next face value equals to 3. The observed is 3. Observed is 6, expected is 10, 6 minus 10 squared divided by 10, and then face value 4, you have 13 minus 10 divided by 10, face value 5, 10 minus 10 squared divided by 10, and then face value 6, 12 and 10, so you do 12 minus 10 squared divided by 10, and then if you want to find out each individual quotient, you can find it in C. Do you see that there is a CNTRB? CNTRB. The first quotient is 0.1, the second quotient is 0.4. But I will just say that is equals to 3.4, and this is the chi-square test statistics. I haven't seen anyone wrote this out in my class because I just asked people to report the value, but it is good to know how you get it. So 3.4, and then how do you get the p-value? So the p-value is the area under the curve, right? On the right hand side. So you have to do this. So you click second, and then you click vars. So second, vars, 2 keys, second key and the vars key. And then you look for chi-square CDF, not PDF. PDF gives you a point on the curve. CDF tells you the area under the curve. CDF stands for cumulative density function. Okay, cumulative. That means area under the curve, CDF. And then once you click the CDF menu, they will ask you a lower limit, upper limit, degree of freedom. So the lower limit is always the chi-square test statistic 3.4, and then the upper limit goes all the way to positive infinity. So to type the 1E99, so you have to type the second key, and then you type the comma key. So above the comma key, the comma is right above the 7 key, right above the 7. Do you see that there is a double E above the comma key? That's why we need to hit the second first. Hit the second and then hit the comma. That is where you get the E. The E is base 10. 1 times 10 raised to the 99 power, right? So that is base 10, and then you type 99. And then the degree of freedom, 6 faces minus 1. And then once you click the paste, they will paste the whole command to the home screen, and then you click enter, you get your p-value. So what happens if you don't see if you don't see a different menu? Because for some older calculator, I know that once you click the chi-square CDF, they will just go to the main menu and then ask you to input numbers. They won't walk you through. They won't say upper, lower, and degree of freedom. So don't panic. Just type 3.4 and then type comma and then type the upper limit and then type 9 minus 1. Just do the typing manually on the home screen. Okay, so that is how you get the p-value. So since this p-value is greater than alpha, we fail to reject the null hypothesis, and then we cannot prove HA is true, right? So that means we are not able to prove that what? Remember this, H naught is fit, and then HA is not fit, right? We fail to reject H naught, cannot prove HA is true. So that means we do not have evidence to prove that this fits into this. We do not have evidence to prove that the observed fit the expected. So that's the conclusion we came up with. Okay, so let me say a few more before I end this video. So there is a comparison between a small chi-square and a big chi-square. So for a small chi-square, which is this problem, so do you see that the chi-square is 3.4 and that comes with a pretty big value? So I want to do an analysis. Maybe you will get this problem on a test. So how do you get the chi-square? The chi-square is you use observe, right? you use observed minus expected divided by expected. You square first, divided by expected. So when the chi-square test statistic is small, that means for each category, the observed value and the expected value, they are pretty close. So this one, the one I wrote, I took the first one, 11 minus 10. So the 11 minus 10 squared divided by 10, 11 is observed, 10 is expected. They are pretty close. So 11 minus 10, that is equals to 1. You square 1, that is equals to 1. So when those two numbers are close, the difference is very small. You square that small number, that number remains small. When you take that divided by the expectation, what's going to happen? The quotient is very small. So you have many small quotients added together. So that's why the chi-square is so small. Just take a look. Just take a look. 8 minus 10, 6 minus 10. Every one of this gives you a very small quotient. So you add 6 small quotients together. Of course, the chi-square 3.4 is pretty low. So that's why when you look for the area on the right hand side, the p-value is so big. So when the chi-square is small, the p-value is big. So most likely you fail to reject the null hypothesis. What about a big chi-square? Big chi-square is the other way around. So that means there is a big difference between observed minus expected. Take a look at this. So you have observed minus expected divided by expected. So observed is 1, just for example. Observed is 1, expected is 10. There is a huge gap between 1 and 10, right? So when you do 1 minus 10, that is equals to negative 9, and then you square a negative 9, you get an 81. So there is a big difference between two numbers, and you square the big difference, and then you will get a very, very large numerator. You take 81 divided by 10, you are going to get a very big quotient. So imagine that you have 6 big quotients added together. So that's why the chi-square is so big. So this one, I gave you another example. The chi-square is 40 something, so 40 point something will just push the cut so far to the right, that will push the cut so far to the right. And since this is a right-sided test, the p-value on the right-hand side is very tiny. So that's why when you have a big chi-square, most likely you will end up with a small p-value, and most likely you can reject the h0. On the other hand, the one on the left-hand side, you get a big chi-square. You get a small chi-square. Small chi-square means observed and expected, they are pretty close, right? They are pretty close. So you get a very big p-value. So most likely that is a fail to reject. All right. So that is the end of this video. If you like it, feel free to subscribe, share, and do whatever you like. I will catch you all in the next lesson. Signing out.